Welcome you all as continuation to our soil water. Today we will read or we will discuss about infiltration and evaporation. First we will start with infiltration. I think this infiltration and evaporation, these are fundamental terms. Most of us know, but as soil science experts, we must know the scientific aspect. So what is infiltration? Simply we can say the downward entry of water. Downward entry of water. This is very simple. If you see, this is a soil surface. This is a wood and rainfall happens or any type of precipitation with heat irrigation. So what happens? Ponding of water will be there on surface and this will entry into the soil surface. So this entry of water is actually your infiltration. Infiltration. Okay, this is very simple, and we also discussed in hydrological cycle after infiltration how the water redistributes itself. Some will go through percolation, where mostly percolation happens in saturated condition. Okay, percolation. Some will move in horizontal way, we know seepage. So our main aim to study today infiltration. So another we will see few terms used in this chapter most oftenly. Another one term which is most often used is infiltration rate. What is infiltration rate? It is very simple. Rate means for time. Infiltration happening for unit time or unit area. We can say the downward entry of water for unit area or unit time. This is very simple. We normally assign with unit millimeter per hour or millimeter per minute, millimeter per second, centimeter per hour. Like this way, we actually assign the units. And another important term, we can say I can give the symbol I, small I. I will use it further. Just remember here, for infiltration rate, I am using small I. And another concept actually, or rather as a term, infiltration capacity. If we want to know someone's capacity, what we say normally? That is the maximum ability. Its maximum ability. Like this way, in infiltration capacity, the maximum rate at which the infiltration occurs. So actually, where it happens? When the precipitation, okay, any form of precipitation, which when normally exceeds the infiltration rate. If normally if your precipitation normally increases more than your infiltration, then we can say the infiltration capacity is reached. Okay, or maximum rate of infiltration now happens. And another term, actually this term was given by Horton. Okay, the scientific name was Horton. And another term which is most commonly also used is infiltrability. This term actually given by Daniel Willett, okay, in 1971. To understand this concept, and coming back to this figure also, you can say here due to precipitation the water is under condensed condition, saturated condition. So what it experiences? It experiencing some atmospheric pressure. When the water is in your atmospheric pressure, it will now, if the soil is in demand, the water will entry from your ponded water to the soil. So this is actually called as infiltrability. The ability of the soil to allow infiltration to happen. When it will happen? If the atmospheric pressure on ponded water will be more, then this will happen. Very simple term. Now I think you get the point. When the water is under atmospheric pressure, okay, simply remember, when the water is under atmospheric pressure, it will allow the infiltration to happen. When the infiltration about to happen, we can say infiltrability. Okay, very simple. Another term we can say steady state of infiltration. From name itself, we can assume what is we are talking about. The steady state means after some time the infiltration will be in a constant motion. Okay, it doesn't change in infiltration rate. So this is steady state of infiltration. Very simple. Another term we will use, which is your cumulative infiltration. Cumulative, you are associated with this word. Cumulative means addition from time to time. Let's assume in first hour the infiltration is your 30 millimeter. Then another hour your infiltration is your 10 millimeter. Another hour your infiltration is your 2 millimeter. Now after 5 to 7 hour, 5 hour, let's assume the steady state now achieved. So we will add all these infiltration rate. We will get cumulative infiltration. Very simple. Or we can either say the depth of total water. Okay, this is your cumulative infiltration. I will assign this with capital I. Just remember small I and capital I because I will use in further our study. Now we will study how this infiltration now takes place. How this infiltration actually takes place in soil. I have said this is soil physics course, so we must draw some graphs to understand the concept. So if I am drawing this graph, I am drawing here. I am taking infiltration rate. Very simple. I have said small I will use for the infiltration rate, and here I am taking time t. Okay, if you plot the graph, you will get this type of graph. What you understand by this graph? In initial few seconds or few seconds rather we say, the infiltration rate was so high, but as time passes, the infiltration rate is decreasing, and at a point it becomes steady. I have already said what is steady. Now here the infiltration doesn't change; it becomes constant. Okay. Up to this, we will actually the cumulative infiltration, and in terms of here only we will also try to understand what is how cumulative infiltration is also happening. If I draw the cumulative infiltration graph, this is also like this one. This is for your I infiltration rate, and this graph is for your cumulative infiltration. You can see cumulative infiltration also with time it was increasing, but at a point of time it becomes now steady. To understand this concept better, actually I think we will use the concept from Phillips equation. He gave the concept in year 1957. He gave two-term model equation in 1957. So what he gives the equation in terms of cumulative infiltration? Actually, he gave the equation where he said cumulative infiltration is a function of your absorptivity and time and function of hydraulic conductivity with time. Okay, we will understand this concept. We will further explain. So, what is S? He said about absorptivity. What is absorptivity? Absorptivity is simply adsorption plus absorption. We already what we are discussing. Most often we use the term adsorption. You know it is a softness phenomenon. To understand this, if I take a dry sponge ball. This is a dry sponge ball. Okay, when water actually attached to the surface, we say what? This is adsorption. And water when enters the volume, okay, entire volume, we will say it is absorption. Now it is part of it inside that ball. Inside it will calculate its volume also. So this is called absorption. So these both are called as absorption. Very simple. So infiltration is a function of absorption with time. If you see the first term, we can see with minimal time the absorptive function is very high. Okay, the infiltration is very high. Now if you see, this is steady state. If you see with the second term, now the absorptivity function has little work to do. Okay, now what the function was? This is hydraulic conductivity. So this infiltration rate is rather a function of hydraulic conductivity rather than absorption at a high time. As the time passes more, then this will be a function of your hydraulic conductivity. He also further simplified this equation as di by dt by differentiating, or we can say it is actually infiltration rate. This simplified st to the power minus half plus your k. This type of equation actually we get. This is also like that I have explained for cumulative infiltration. You can assign it also here. Okay. Initial it was function of absorptivity. Later only the function of hydraulic conductivity. From this equation we will better understand this graph. Okay. That's why I have taken the example of this equation. There are many equations available, like your Green and Armed equation, which actually followed the Darcy's law to derive the equation. And I forgot to tell one thing. He actually used that Richards equation. We discussed unsaturated water flow, Richards equation. I have dictated you what is the equation. So he actually used the Richards equation to derive this type of equation. Now, as we move across, he also said as the time passes more, okay, your I is equals to your hydraulic conductivity. Okay, he derived it. He said as the larger values of t, or we can say more time passes, this will be infiltration rate will be more function of your hydraulic conductivity. Also for horizontal infiltration, as in case of Darcy's law also, we said gravitation is nullified like this way. In horizontal infiltration, he just nullified this. Okay, he just said that your I is s into the power half. For horizontal infiltration, he derived this type of equation. Okay, simply now, if you want to calculate the absorptivity function, you can calculate from this. Your cumulative infiltration for upon time half, or you can say root over of time. This equation, through this equation, we can derive the absorptivity function. Now, we will go for another important concept. We will see how the moisture distribution now happens during infiltration. How this moisture distribution happens? I have already said as the ponding of water or saturation or irrigation happens, the water will move downwards. Now, if you want to see the moisture distribution, okay, distribution during infiltration in a homogeneous profile, homogeneous soil profile. Okay, we are taking homogeneous. Now, as I have already said you, this is your surface, soil surface. This is your soil surface. Ponding of water happens. Before infiltration, there must be some precipitation. We know already. So what will happen? There will be to go to depth. This is your depth. We are moving from surface to vertical. So the depth is increasing this way. And here it is volumetric water content. Theta, volumetric water content. Or unit is centimeter cube per centimeter cube. This way is actually derived. This way actually giving the moisture distribution. So there will be first due to saturation, there will be one very thin layer will be created, which is known as saturation zone. This zone is actually your what? Saturation zone. This is your saturation zone. We know what is saturation zone. All the pores you are filled with water. There will be no air. Maximum free flowing water will occur in this region. Okay. It is very few centimeter or few millimeter as we say. Okay. Few millimeter. Now, as the moisture content now will decrease, moisture content with time will decrease. There will be another zone came which we will call transmission zone. This is your transmission zone. Actually, this zone normally what it does, it just transmits the water from your saturated zone to next zone. This zone actually, this after transmission zone, one zone is created. This is actually most important zone because this lengthens this moisture distribution. We call it as transition zone. Transition zone. We call this as transition zone because this actually lengthens, or we can term it as lengthening zone. Here also moisture content decreases compared to your saturation zone. Okay. Now after this transition zone, the water content now decreases more abruptly. Okay, so there will be another zone created which we can term it as wetting zone. Wetting zone. And this conceptual line, okay, imaginable conceptual line, we can call it as wetting pond. Wetting pond. Actually, this pond actually decides your differentiated your wetting zone and your dry zone. This actually differentiates between your wet zone or moist zone, okay, wetting zone and your dry zone. This is very simple. From this graph we can understand, and always remember this is one of the important zones, transition zone, because this is the lengthening zone. Okay, and moisture constant we can see constantly decreasing with the depth. And here we can say another thing that your wetting pond is not always same for all soils. It is not same. It may, for an example, this is a sandy soil. Okay, now the clay soil, the wetting pond may be more or less, because the infiltration will be more or less. Sandy soil, the macro pores are more, the pores that are more infiltration may occur. This is very simple. But in clay soil, the infiltration may take more time. So the wetting pond, like this way, this wetting pond is main important actually. This type of zones actually created. This is the moisture distribution zone. You understand? This type of zones actually created with different soil groups. Now, as we have want to know how this infiltration occurs, we will see the factors affecting infiltration. This way we can decide the wetting zone, wetting pond. The wetting pond will decide. What are the factors now affecting? The first factor always we take it as texture. What are the factors affecting? Factors affecting infiltration. Okay, I will say rather say infiltration rate. It will be easy for us to compare. And first factor is your texture. So infiltration rate will be higher in which type of texture? It's very simple. In post texture soil, it will be higher compared to your fine texture soil. This as a soil science student, this is for us the layman thing. Okay, I can say very simple. And in case of structure, this is also very simple. In case of your spherical structure, this will be most. The infiltration rate will be higher compared to other structures. Okay, very simple. And coming to another important property, which is organic matter. If the presence of organic matter is there, then there will be structure development will be good. Okay, microorganism activities will be good. So this will encourage your more infiltration. Very simple. And another factor, if I say compaction, if compaction increases, as we have discussed, in compaction what happens? The surface sealing happens. Because of your larger rock fragments, larger rocks break down to smaller fragments, the finer particles seal the pores. So this will be a high ball density layer. Okay, because of high ball density, this will reduce your infiltration. As compaction increases, your ball density increases, your infiltration rate increases. Very simple. And another one is your rainfall. If you say very high quantity of rainfall happens, very high precipitation will give more quantity of irrigation. So what will happen? The infiltration will reduce, and the infiltration capacity will be reached within few time. Okay, very simple thing. But the tricky part is we will normally think more irrigation, more infiltration will be there. No, if your rainfall is more uniform, rather we say more uniform, then your infiltration rate will be more. If it is very abrupt or turbulent flow of water will be there, okay, that way your infiltration will be reduced. Very simple. Another one point, I can say vegetation. Vegetation will all know, if vegetation will be there, okay, the runoff losses, all those seepage losses, this will be less, so more will be infiltration. If the soil is bare, no vegetation are there, so infiltration will be less. And from another property is porosity. Another factor affecting, you can say porosity. If soil is more porous, okay, then the infiltration will be higher. Like this way, you can say another factors are there. I am discussing it. You just go through this. If we want to quantify, now we have learned what is infiltration, how it decreases with time, equation, and your moisture distribution factors affecting. Now if you want to rate this, if I want to know is very high infiltration is occurring, low infiltration is occurring. In natural way, actually for infiltration to happen, your rainfall and irrigation are important. But in artificial also way, we can measure this by doubling infiltrometer. At field condition, we actually use this ring infiltrometer to measure the infiltration rate. I discussed in practical class about this. I have actually done this type of experiments already, so I will explain it in a better way. Don't worry. Just remember now, to measure this infiltration rate, we will use double ring infiltration. Through this, we will give a rating chart so that we will know how much infiltration is happening. For classification, I will say if the infiltration is very rapid, okay, then the value will be, or if the infiltration rate in millimeter per hour. An infiltration rate in millimeter per hour, I can say is more than 254. Okay, and if the infiltration rate is rapid, the value may be 127.27 to 254. Moderately, if the infiltration is moderately rapid, we assign the value is 63 up to 127. And if the infiltration is moderate, we assign the value 20 to 63. Then if moderately slow, we assign the value 5 to 20. And if this is slow, the infiltration is slow, the infiltration will be 1 to 5 millimeter per hour. If it is very slow, now that time normally we can say very steady state. Here the flow will be less than 1 millimeter per hour. Now from here we can say 7 classes. Sometimes this type of memory based questions may be asked, so that's why I have written. Okay. Now we will come to our next concept, evaporation. This evaporation actually most of us know. Even I can say all of us know. What is evaporation? Evaporation is simple. The liquid gets converted to gaseous state. You know what is evaporation? This is very simple. Evaporation is your liquid converts to gaseous state. When this will be gaseous state, this will losses happen. But here one question actually most often asked, but in my UG days I also get confused. Like, what is the difference between if evaporation is there and your condensation is there? Which one is your exothermic reaction? Which one is your endothermic reaction? You say your evaporation actually is your endothermic reaction. This remember, this is most important question. Okay, and your condensation is actually exothermic. To understand this, we can take example of us also. You see, when we work so hard, okay, we use more energy. What will comes out? The sweat or pasina we say. This sweat actually coming out because of endothermic reaction. We use energy. So this creates actually cooling condition. Cooling conditions. Okay, evaporation because of endothermic reaction. In condensation, actually this creates slightly warming condition. Okay, because the heat is released, you try to combine or condense two states. Then there will be exothermic reaction. The energy will be comes out, so this will be warming effect. Remember this way. Now coming to our topic. To start this evaporation, actually some prerequisite conditions are required. Some preconditions are required. Because without preconditions, this evaporation will not start. You know already. This is very important. One is your heat. Okay. Continuous heat supply. We will rather write continuous heat supply should be there. Heat supply. We where we have observed this now in northern states, in northern India, we can say the temperature is so high in May, June. Most of the evaporation occurs in those months, and also in a part of the day, if the temperature is more high during noon time, more evaporation occurs. So continuous heat supply must be there, and a simple thing we must remember also, that is the latent heat of vaporization. Then to convert that water to a vapor, latent heat of vaporization. I think some of us also know this. We have also read that in our lower classes. It is 580 calorie per gram. Okay, at 20 degrees centigrade. If the temperature increases, this latent heat of vaporization will be decreased. Like here 540, it will reach 540. If you increase the temperature to 100 degree. Okay, very simple. Another precondition is your vapor pressure. Vapor pressure gradient. That I can say vapor pressure gradient. Vapor pressure per unit depth, we will say gradient. So you just, these are very simple points you should remember. If the rate is there, then there will be time assignment. If the gradient is there, then there will be length associated will be there. Divide this vapor pressure with your depth, this will be vapor pressure gradient. So how this vapor pressure gradient creates? We already discussed when water is now this is a condition of water. Okay, and it is an atmospheric pressure, and if the surface soil here, because the pressure is higher, the water will move downward, and in case of evaporation, as this water now dries up. So but here in surface soil your water is there. Evaporation is actually mainly a surface phenomenon. Don't think it will happen in subsurface region. Okay, the initially dry soil, some moisture content will be there at the surface soil. So as this vapor pressure here of water is higher compared to your atmosphere, so what will happen? The water will evaporate. Very simple. I am not complicating these things. It is very simple. I think most of us know. These two factors actually provide the energy for this evaporation to happen. And this vapor gradient, pressure gradient is actually your what? Affected by factors like temperature, your humidity, wind velocity, etc. Okay, and another important one is there should be continuous supply of water. Okay, from subsurface. Continuous supply of water from subsurface. We already know this point. When plant requires water, what it does? If the rainfall is not happening, we are not applying irrigation. It draws water from subsurface layer, subsurface layer, or rather we say bhados zone. Takes its water from where? Capillary filtering zone or saturated zone. If the saturation zone or underground water is your more, then more supply of water will be there. More evaporation will happen. This is very simple. Continuous supply of water should be there. These are the preconditions. Now, if we see scientifically the various stages of evaporation, we'll see various stages of evaporation. Actually, this class I think the most easiest class. Very simple concepts. We already know this. If you see the stages of evaporation, your the y-axis I am taking evaporation rate, and x-axis I am taking time. Okay. Now, what happens? I have already said in infiltration like this way, evaporation is also. You at very initial time, the evaporation will be more, as there is saturated water content. So, this type of zone actually, this is, you can say, this is the first zone or stage 1. Okay. We will define those zones. First we will draw the zones. Now, after evaporating from first zone, now the water content decreases such abruptly. It reaches the second zone. Okay, you can say this is the second zone. or we other running stages, first stage, second stage. Okay, you can name them also like that way. Now at third stage, third zone or third stage, we can see the water content is nil, almost nil. We draw little bit downward, and then assume that there water content is now with time your evaporation rate is actually almost nil. Here the evaporation rate was higher with more water content. As the water content increases or moisture content decreases, the evaporation rate also decreasing. So if we study stage wise, in first stage we can say that is under saturation. So it is actually weather controlled stage. We can say it is weather controlled stage. Weather, or rather we can say climate controlled stage, can be controlled by climate. This is very much known. Okay. Like your in sunny days, if more evaporation happens, the your clothes will dry faster. But when the evaporation is less, we know the dresses will not dry faster. Okay, this is very simple. Weather controlled stage, and also this stage occurs in sandy soil. In sandy soil, there can be few hours. This stage can last for few hours. In clay soils, we can say this stage may occur for few days. This is also very simple to follow, I think. And another point we say, as the water is evaporating, okay, and we will study the Darcy's law, that Q equals to minus K dH by dZ. If the hydraulic conductivity is decreasing with evaporation, your hydraulic gradient will supply the water in this stage 1. Okay, remember this hydraulic thing so that it will be easier for you to understand. As the first stage, the more evaporation is happening, the hydraulic conductivity that decreasing time to time, but this will be supplied by your hydraulic gradient. Okay, and coming to second stage, we can say this is more of profile controlled stage. Profile controlled stage. Here the moisture content is very less compared to first zone or first stage. Now here for sandy soil like this way we can say few days. Clay soil more few days, because this is happening later, so it will take more time for this to happen. And this I have discussed that here the hydraulic conductivity while decreasing, okay, this your hydraulic gradient actually could not supply the water. Okay, this could not actually supply the water to follow the hydraulic conductivity. Okay, in this way I can write, it will be easy to follow you. Okay. This is very simple. And in third stage, we will say the water now in a vapor stage. Okay, now the water is in vapor stage. The water is not free flowing, and at some time the water will just decrease to 0. And I forgot to write one important thing. Actually this zone 1 is called as constant rate stage. And actually this type of memory based things we need to remember, because it is easy to understand and follow, but we need to remember this type of memory based things. Maybe asked in our exams. Any competitive exam, NET exam, ARS exam, may be asked. Like this second zone or second stage, we can say falling head stage. Falling rate stage. Sorry, falling rate stage. And this third stage we name it as slow rate stage. Slow rate